Now, we had talked about plate girders last time. And I don't think, I guess we'll go through this, cover it quick, what we talked about before. Plate girders are just like any other girders. They're not, they're actually can be very overwhelming at first. Okay, can be very kind of scary at first. Because you're like, whoa, I've always had this manual, and this manual has always helped me make these decisions. And now I can do whatever I want. But we're still going to give you guidance, okay? We're still going to get you there. And I'll tell you, plate girders used to be really, really hard to do. Even 10 years ago, they were really hard to do because the AISC manual was just written in such a way that it was a total disarray. I mean, it was just a mess. Okay, but they've done a much better job of reorganizing it. Plate girders are no different than any other girder, except for now you get to decide what size you want your flanges and web to be. Okay? You can also make up funny sections like this. Why would you ever want to do this? Well, you can get so much more bottom flange out of this, right? So much more bottom flange out of some structure like this than you can out of using two of these shapes. Okay? The idea, the concept, is to optimize the steel plate thickness to match expected loads on the structure. Sometimes we modify these yield stresses. Okay, typically the span lengths for 70 to 100 are for simple spans, 70 foot to 150 foot. Well, why do I tell you that? Because if you shouldn't even think plate girder until you get above 70 feet. Shouldn't even come into your brain. Okay? Should be rolled, 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 rolled. And I'll explain why coming up. Because it's cheap. Okay? You might say, but oh, Dr. Lay, I can save all of these, I can thin all of these down and make them so thin and light, and that's money, right? Sure it is, but there's a lot more inspection that goes into plate girders. There's a lot more welding that has to go into plate girders, and welding inspection is extremely expensive. Extremely expensive. At least if it has to be done with x-rays or if they have a non-visual or non-surface welding inspection. It's very expensive. And most bridges do. Most bridges do. And most buildings should. Okay, now when it comes to continuous, I mean, you can get up to really long spans with a plate girder, something like 350 to 400 feet, if you can get these counter spans to balance them. Okay, and it comes down to deflection starts to control in these longer spans. Now, this is a real piece of advice. This is really important. If you want to become a really good designer, you need to understand when things typically control. And you need to go there first when you're doing your designs. And that's what you need to use to bracket or start you someplace. And then just check everything else. Because what happens if you don't do that, if you don't start without what's important, you'll be spending way more time coming up with a design. You'll design something that you think is going to work, and you'll be like, oh crap, that didn't check. And if you realize what's important to begin with, then you can save yourself a whole lot of time. And time is money in the engineering world. Okay? When you get to long spans, deflections, control. Okay? What do you need for deflection? Eye. That's all you need. Eye. Okay? We're going to be doing all of these crazy calculations to get plate sizes and stress sizes and things like that. If you're in this criteria where you have long span bridges, save yourself a whole lot of trouble and make sure you're starting with an eye. That will help. An eye that will do what needs to be done. Okay. Recall. Like a pirate, right? Aye. Recall the following flexure limit states. Hey, we've talked about this in the past. This is no different. This is 3 of the Snell charts of apocalypse, right? We've got the lateral torsional buckling one. Oh, boring. The one we've seen before with the flexural local buckling a little bit. Okay, local web buckling. These are now going to become big issues when it comes to plate girders. We're going to have one more that we hopefully get to today. The cool thing about these is they're all about some kind of slenderness ratio. It's all about that. This just happens to be L sub B, right? Unbraced length. This happens to be something similar to L sub B. Not quite. It's L sub B for a top flange. B sub F over 2T sub F. This happens to be some other slenderness ratio, H over T sub W, for your webs. Okay? And here's your gamma P's and gamma R's. Okay? There's your phi m sub P and phi m sub R's, and I left out a 0.7 right there. Okay? No big deal. This is cool. It's very, very important to understand where you are on these charts when you're doing a plate girder design. I'll say that again. It's extremely important to understand, am I here, or am I here with my flange? And as I make this decision, where is that going to push me? Is that going to be a linear change? Is that going to be no change? Or is that going to be a non-linear change? Again, it will save you so much time. I mean, people, once you get good with this, you will blow away people with spreadsheets that say they can do plate girder design. You will kill them because you will truly understand what's going on. They're like, oh, I can write a spreadsheet for that. It will take you longer to come up with a spreadsheet to do this. There's too many if-then type statements going on here. Okay? And wouldn't you rather just know what's going on? Wouldn't you rather understand what's going on? Okay? Okay, I'll tell you a story. When I worked at TxDOT, we used to have design races. Okay? Because I used to design everything by hand. Everything. People would be like, oh, there's a computer program for that. I was like, oh yeah? They're like, yeah, it's $15,000. And I had said, okay, you get your computer program, I'll design it by hand, and we'll see what's going on. Okay? I was done on 2 pieces of paper. 2 pieces of paper in an hour. It took them a week and a half to figure out how to even put all the inputs into the computer program. Okay? And guess what? We got the same answer. They were like amazed. They thought like it was like some act of God that somehow we got the same answer. I was like, they're using the same equations I am. I just know what's important, and the computer program is an idiot. Right? It just has to check everything. 'Cause that's what they do. That's how they work. They check everything. But if you know what's important, you don't have to. We used to have all kinds of races. Okay? When we did column design, and we had 10 columns we designed, and they were all reinforced concrete. I did them in like 3 hours. Okay, on about 20 pieces of paper. Okay, took them 2 days. Okay, with a computer program, PCA column. If you know what's going on, you can kill designs quick. Okay, now let's keep talking about plate girders. Recall from design of rolled sections that for long span structures, the shear capacity never controlled. Do you ever realize that? You looked up phi VN. You looked up phi VN, and it was like, it's like you didn't even know why you were doing it, because it was often 3 to 4 times higher than you ever needed. Well, you check it, because that one time you didn't check it, it will be important. But I'll tell you when it is important. In short, very, very short span, highly loaded structures is when the shear can become important. Okay? Never, ever in long span structures should shear ever control. In concrete or steel, unless something else is going on, something weird's going on, like you're really thinning things up. Okay, you're really, really thinning things up. And that's what we're going to be doing with plate girders. Okay, so recall from the design of rolled sections that for long span structures, the shear capacity never controlled. And you should realize these things. You should be looking at these things. You should be having a feel for these things. You're not just passively doing design. You're active. You're thinking. You're part of it. Therefore, the web is typically the portion of the girder that engineers often push to optimize when it comes to plate girders. Previously, we did this example. We used a W30 by 173, and we showed it was satisfactory for a simply supported girder, supported at the end, 150 kip live load. We found our MCP was 2280, which was just above 2138. We found our FVN was about 600 kips, which dwarfed our capacity. Okay? Our I sub X we needed was 8230. We provided something like, or we needed 5027. What does this tell me? This tells me I'm right up against the limit on MCP. Right? This tells me I got plenty of I sub X to spare. And this tells me my FVN, oh my gosh, I got money to burn. Right? I got steel to burn. So let me see. If I decrease the size of my web, what's that going to do to my moment capacity? Almost nothing. Your answer should be almost nothing. Why? Moments carried to my flanges. Webs does almost nothing. Not nothing, but almost nothing for us as far as just section goes. Right? So we ought to be able to reduce web and still be okay. How about I sub X? Well, does web do anything for I sub X? Very little. What's I sub X? What's I? What does the moment of inertia measure? Yeah. What's a sentence that tells us what moment of inertia really measures? It is a mathematical quantification of the area away from the neutral axis, is what I sub X is. And if you ever find yourself calculating numbers where you don't know where they are, you're doing something wrong. Okay? You're doing yourself a disservice. You need to know what these things mean. Okay? It's important. So I sub X, 8230. I don't think changing my web is going to affect me at all. Almost nothing. Okay? Almost nothing. So, theoretically, we could reduce our web, and if we use this ratio here, by around 80%. Now, don't do this, okay? This is not the correct step to decide on how to reduce your web, because we're going to find out that other things are going to end up controlling, okay? Okay? So don't do this. But this is just kind of for pictures, okay? This is just for an introduction. Okay, this is ideal. It won't actually work, but for now, we're going to go with it, okay? Because if you remember when you calculate shear is primarily a function of area of your web. That's what it's a function of. The area of your web. Flanges don't help for shear. Not much. Actually, almost none. Okay? So we started out with something like this. This is that rolled section that we were talking about. And we ended up, if we reduce 5/8 by 80%, we could use a 1/8 inch thick web. What's the number say? Again, this isn't going to work. Okay? You can hopefully look at it on the piece of paper. And I recommend you draw these things all the time. What you're proposing for people to use, I recommend you draw them to scale to get a feel for what these things are. Okay, but we're talking about, that's 30 inches. It's almost 3 feet. 3 feet deep. Okay? And we cut it 1/8 of an inch thick web. 1/8 of an inch thick web. That's what the math is saying will work. And that's why plate girders are so appetizing to people. They're like, oh my God, look at this. I can go from something like an original weight of 173 pounds per foot. Using this new technique, with my new weight, I can get down to 114 pounds per foot. Wow. That's a 34% decrease in weight. If we assume steel is about 3 pounds per foot, $3 per foot, pardon me. $3 per foot. Now that's not including welds, that's just finished steel. Okay? Finished steel. That's not welds, that's not weld inspection, that's just for cutting plate. Okay? $3 per foot. That's a $60 per foot savings. Oh, that sounds really exciting. That sounds really exciting. And I say, man, if it was only this easy. It's not. But this is what gets people excited. And this is what gets people who like to calculate things, people that like to try to shave off weights and things like that. This is what gets them excited, seeing numbers like this. It's not that easy. Okay? It's not that easy. Slender webs can cause problems. Now, just because things aren't that easy doesn't mean they're impossible to do. We can make this happen if we really want to, but I will tell you right now, if you can ever use a rolled shape versus a plate girder, use the rolled shape, at least in this country. Okay? Our inspection costs and our labor costs are way too high. Okay? Just way too high. Do something like that. Okay. I'll hammer that home later on. If the web buckles in the plane, then it can't carry the assumed amount of bending moment. Okay? If the web starts to buckle out of the plane, then it can't carry the assumed amount of bending moment. And that's not that big of a deal. Okay, we're going to find out. One job of the web is to actually prevent the flange from buckling. As the web starts to yield and buckle, then the ability of the web to brace the flange diminishes. This is a really big deal. If your flange buckles, when something buckles, what does that mean about stiffness? 0. Cero. Nada. Nunca. Stiffness is 0. What does that mean? Really high, scary deflections. Okay? The web can also buckle due to shear, and we're going to talk more on this coming up today. Buckling issues in the web can be satisfied by adding our friends the stiffeners. Okay? This may seem simple, but can be costly. Imagine every single, let's say we have a weld here. Let's say you have a weld here. Every one of them's got to be x-rayed. If you're going to have to add a stiffener, why don't you just go with a thicker web, right? Well, and that's where you're going to do the math, and you're going to figure out what the trade-off is. If I can get away with stiffeners at this spacing, then it might be economically worth it to thin my web up. Does that make sense? Those are the what-if games that you're going to be able to start to play now as an engineer. Okay? That's what you're going to have to do. Now, there is this maximum H over T sub W, and it's kind of silly. It's something you need to put in your notes and think about. But they're kind of silly because they're set at some pretty extreme limits. This 12,200 over Fy is the one maximum H over T sub W. And then with a stiffener spaced less than 1.5 times the depth, it's 2,000 divided by square root of Fy. So this is, if I have stiffeners, so this is my girder, and there's spacing on my stiffeners, this spacing we'll call S. If S is less than 1.5 times my depth, which I guess is h in the steel world. If S is less than 1.5 h, then I get to use this limit. That's as thin as I can go. Okay? Okay. And believe it or not, for that example problem we just worked, the one that was like totally absurd, that I would never ever do, it even satisfies this limit. Okay? So what I'm getting at here is that it satisfies this maximum h over t sub w. That doesn't mean it's going to satisfy 1, 2, and 3. Okay? It just means this one maximum h over t sub w. It's not going to have an impact on. What I'm trying to get over to you, what I'm trying to communicate is, now everything is about to affect everything. We're pushing the limit so far with our web, slimming it up so much that now what we said earlier about the web thickness not impacting our flexural strength is wrong, because if our web starts to buckle, then we don't have the same capacity we had in the past. We don't have the same M sub P we had in the past. We have buckling starting to occur. We have a different failure mode. Same thing happening here. If our web gets thin enough and our flange starts to waving at us, that is bad. You with me? Okay. Okay, more fun. Okay, so hopefully that makes sense to you. Hopefully now we're getting this idea and this concept that when we thin our web up, really push things, that we're going to start to impact other parts, other things that we've assumed to be okay in the past are now going to change a little bit. So now we're going to talk about shear capacity first, and after we cover this handout, we will dive into full-on crazy plate girder design. Okay? This is like the last step. Okay? So I've kind of introduced this concept. I'm going to cover how we handle shear, and then it'll be like right up, full-on plate girder. Plate girder ninja. Okay? What's next? So, recall that all webs in rolled sections were compact. This made shear design very straightforward, as the shear capacity was just 0.6 Fy times A sub W. We actually had a phi factor in there as well, but 0.6 Fy A sub W. And we also had a C sub V, but C sub V was 1. Was always 1. Was. Not anymore. Not with plate girders. Okay? But in the past, with rolled sections, it was always 1. The behavior starts to drastically change if the web of the girder becomes thin. So let's just say I take a simply supported beam here. I put in the load on it. I have my shear diagram is going to look something like this. My moment diagram is going to look something like this. And I'm going to go to this. I'm going to zoom in, blow up this point, this circled area right here, and call it detail A. Okay? Detail A right here. And I want to talk about the stresses on the cross section at this unit, at the center of the girder. Okay? This unit. What stresses do we have here? Shear! Yay! And if I have this element, what's it going to look like? What do shear stresses look like? It's going to go down on this side. What's that? Up on the other side. And what? Right on the bottom. Left on the top. And they're all going to be equal, right? or tau. Equal to tau. So let's call them tau xy, something like that. Okay, this is what we call pure shear. Now, how about, is there any axial load? Is there any bending stresses on the element? Not in the middle. How'd you know? I know it's obvious to you, but I don't know if cyberspace it's obvious to them. So it's where the neutral axis is, right? So in the stress diagram, we would assume at the center to be 0. The shear diagram, at the center, assumed to be a maximum. You should know that. So now let's say I rotate this till I get principal stresses. Remember doing that? Yeah? What are they going to look like? Well, I'll make this go faster. I mean, you can think of like this. Think about adding these two together. What's the component going to look like? It's going to look something like that, isn't it? And adding these two together. And the component's going to look something like that, isn't it? So what do we know about what's going to happen on these faces? No? Now, if there's a principal stress, that means it's the point where you have no shear, right? You have to have equal and opposite if these are all the same. All these values have to be equal and opposite. Or if that starts to blow your mind, it has to look something like that. Okay? Well, that's cool. That's the center, right? What's going to happen as I go up? Well, this is going to start to have some axial load on it. These are going to start to, the rotation's going to, as I move upward, the element's going to start rotating that direction. And as I move downwards, the element's going to start rotating the opposite direction. Oops. The opposite direction. I believe that's right. I think that's right. Okay, that's cool and all. That's neat. Let's talk about, what if we had a truss? Right? What if we had a truss? Instead of this is a very strength of materials type approach. What if instead of thinking of it like this, what if we thought of it instead in terms of a truss? Okay? Sort of a truss. So if we have this as our truss element, is this a stable truss element? Well, we remember truss elements all have pins, right, at their nodes, right? And if you put this stress or this load on this truss element, what would you expect to happen? It would fold up. It would rack, wouldn't it? It would rack. So what do we need? What is this truss missing? Braces. Yes. Braces. So I'm going to put some braces in. And I'm going to think about it in the dead center here. Dead center. This is what the element looked like. In a truss, what do we do instead? I mean, what do our braces usually look like? They usually look like diagonals, don't they? We usually have one diagonal that goes from one side to the other side. And the other diagonal that goes from one side to the other side. So in this element, with both of these braces in, which of the braces is in compression? Brace 1 or brace 2? Brace 1. Brace 1 is in compression. Brace 2 is in tension. Has to be, doesn't it? How did you know? Well, think about this principal stress. principal stresses are oriented like this, it looks something like that. If that doesn't make sense to you or freaks you out, think about this trying to be racked downwards. Think about holding this one still and racking this one downwards. If that's going to happen, this area is going to want to compress, and this area is going to want to pull back. Pull in tension. Okay. So this is what we call the equivalent truss explanation. And what I say here at the bottom is if this element is thin, or if these braces are really, really thin, and our girder is tall and thin, then we can have stability problems. Hopefully you can see that. Hopefully you can see where compression usually causes stability problems, doesn't it? Right? Stability means buckling, doesn't it? Okay. So if compression causes stability problems, we could see we're usually probably thinking about calculating what the stresses are on a truss, but we could also treat them as columns, and we could calculate what the buckling capacity was. Right? Right? Well, what does this look like on a plate? What does this look like on a plate? Okay. Everyone looks at me like I'm crazy. So I'll prove to you that I'm crazy. Now this class charges some very high tech fees. Doesn't really, but this class charges some tech fees, so you can have the best in teaching it. This is a sandwich bag that I have cut in half, and I have taken some very expensive magic marker and drawn a grid on them. Okay? And this is just like our truss model. And I'm going to take my right-hand side here, this is my left-hand side, and I'm going to rack it downwards. Holy cow. Look at that. What's going on? What's going on? Good answer. What's going on? What's happening?
You see there's like a clear place where it's tension and a clear place where it's compression.
Clear place where it's tension and compression.
It's wrapping.
Point. Come here and point to me. Point. What's going on here? That's in tension. Where's the compression happen? What do we know happens in compression? Buckles, right? Where do you see buckles at? Here, buckles. Point to them again. Cyberspace and signals. Buckles. Sure? I'm sure it is spectacular, isn't it? Okay. It's buckles, right? Buckles. You see it? Yeah. Got it? Buckles. Oh. So when you were looking at that sandwich bag, and I don't know how well cyberspace could see it, but hopefully the rest of you were closer than others, there were some tension in this direction, and there was compression in this direction, and there were buckles. Uzz. And we're going to imagine that we're back to where the very first buckle happened. And if I was really, really good, maybe I could do it on this. If I was really good, which I'm not, but if I'm really good, and as I move this, I can get just one big buckle to happen. Kind of see right where that cross is right there. There's one big buckle, and then there starts to become 3 or 4 buckles, a bunch of buckles. See that? And we call those old modes, different modes of buckling. Okay? different modes of buckling. But the very, very, very first mode creates one big buckle. One big buckle. So if we drew like a cross section at C, and a cross section at B, and a cross section at A, what we would see is at C, it's a small amount of buckle. At B, it's a larger amount of buckle. And at A, it's the largest buckle. Now, what happens is that we might not ever really get to A. We might, well, we would, but we wouldn't get to A everywhere. We'd get to A, and then all of a sudden, instead of buckling like this, it would prefer to buckle like that. Because it actually takes less energy. It takes less energy for that to occur. That's why it happens. It'd prefer to do that. And we could spend class time working out differential equations to prove that, but why? Hopefully you can take my word for it. And if you don't take my word for it, then watch my sandwich bag. Because it doesn't buckle that way. I can clearly see 1, 2, 3, 4 or more buckles. Just turned off. So, I guess that's it. Got the most out of that sandwich bag, though. I swear, I was sitting in my office and I was like,